Hello and welcome to Pre-Calculus. The goal for today is to learn about inverse trigonometric functions, as we see up there by the title. And what you see here on the screen already are some basics. We would say sine of pi over 6, which is 30 degrees, is 1/2, and that will be trigonometric function. Now, when you flip domain and range, input and output, you get inverse trigonometric function, which we denote with sine -1, right? So sine -1, and we read it sine inverse of 1/2 equals pi over 6. So you see that the input and output swapped, just like we learned in 1.8, right? They're supposed to be swapped. Now, there are better notations than this, which is the arc sine and a sine. Those are better notations. They are not used in too many places. In Europe, we usually always use these, but here they're not really used. And the reason why is you can't confuse this -1 with like 1 over something, because it's not it, right? Inverse function is not the same as 1 over function. They're a completely different world. Now, arc sine, inverse sine, inverse cosine, and so on, we use the same chart of values. We just read it backwards, right? So earlier, you would say, how much is sine of 60? And you would go and you would find sine, and you would find 60, and then you would say, oh, they intersect at √3/2. Now, you say, how much is the inverse cosine of 0? Okay, here is my cosine, and the 0 is here, therefore you go up, and it's pi over 2. So it's backwards, right, from what you are used to. I listed all 6 inverse trig functions. So this is what they inverse trig functions. So this is what they look like. And the input is the number, and you get angle as the answer. And I do have these, what I call mathematical sacrilege. This is why I put a quotation marks. So sine of an angle is a number, and that's like saying sine of pi over 6 is 1/2. But over here you have inverse sine of 1/2 is pi over 6. So it's backwards. And we did this one example, example 9, in which I gave you the √2/2 values, right, are happening at pi over 4, and then we were looking for the cosine of a negative √2. Cosine of a negative √2 was at 3 pi over 4, so that was our answer. So let's take a look at more of these types of problems, and then take a look at graphs, and then we're done with this inverse section. It's a really long section in the book, so I'm gonna flip through pages. There we go. Problem. So we did number 9. How about problem 17? Tangent inverse of negative square root of 3. So we have a couple of options. One of the options is to realize that the tangent is the odd inverse tangent, is the odd function, which means that you can kick the minus sign outside. So minus tangent inverse of √3. And the explanation is tangent inverse x is an odd function. All right, cool. So now, if I go and look at my chart, what is the value for inverse tangent of root 3. So inverse tangent of root 3 is pi over 3. Awesome. So answer is negative pi over 3. Now, does that make sense? Well, you can check that using the unit circle and then figuring out the negative pi over 3 is right there. So negative pi over 3 is the same as 5 pi over 3, right? It's the same value. So you can do that, and all students take calculus. So calculus is positive, cosine is positive, sine is negative, and tangent, obviously, as a division, is negative as well. So if you look at this, right, you will have your reference angle R as pi over 3, right, because the closest x-axis is the positive x-axis and it's pi over 3 away. And the tangent is negative. So here is your negative and here's your pi over 3. That's what we have, right? So there are many ways in which you can get to this. One is through looking at the chart of values. One is about knowing the circle, the unit circle, right? You can also compute sine and cosine and then divide them, right? Because we also learned that the tangent theta is sine theta over cosine theta. So you can divide the values. There are a lot of different ways in which you can get there. Now, they also have calculator use, and the whole section of problems for calculator use. And this is very important because of engineering. Your engineering problems and physics problems, they like to see those degrees. And mathematics doesn't. Right? We like to see radians because the formulas work with radians. Now, in physics, the formulas also work in radians, but you always convert them. So, you need to know that your calculator can do both. If you didn't know, right? Calculator can do both. And if you use the button called mode, you will be able to switch between radian measure and degrees. Right? So one or the other. Now, this is where you go for graphing. So anytime when you use the calculator to graph a function, you can't see it on the screen. Most likely your mode is in degrees because you had the physics class or engineering class. And now coming back to math and trying to graph a sine of 3x over 4, it's just not on the screen, right? So make sure you change it to radians for graphing. Now, the problems say, give the degree measure, give the radian measure, then you still have to switch between modes. I used to joke with my students, the only way I know that you are a good Precalc 2 student, right, the Trig student, is if by the end of the semester, the only key that faded, right, and you can't read what's on it is the mode button. Because you literally have to check in every single problem if you are in a right mode, because calculator will compute values no matter what. And if you are in a wrong mode, it will give you different answers. And then good luck. And it doesn't display units, calculator, right? Doesn't display units. So if you don't know before you do the calculation which mode you are in, you might get the wrong answer because the problem was asking for degrees, you put down the radians, and they're vastly different. Let me give you the example. So, for instance, if you take a look at the inverse cosine of 3/8, right? What is that? Well, there will be two answers. The first answer, since I am in radians, I'm going to go and say inverse cosine of 3 divided by 8. And my answer in radians is 1.186 radians. But then, if I switch the mode to degrees and do the same calculation, I will get 67.98 degrees. Now, this is not included on the calculator, so, right, good luck. You have to be very, very careful, and you have to check the mode before, right? You have to check the mode before you do the calculation, so you know that you are coming up with the correct values for your problem. And the entire section, like problems 19 to 30, they're all there for you to just shove the numbers in and get your values. So there you go. Okay. And now we're going to take a look at a particular type of the problem where we get to combine trigonometric functions and their inverses. And one thing that you could bring back all the way from 1.8 was that when you combine an inverse with the original function, right, which is f inverse of f of x, you will get x. And when you combine function, well, compose, not combine, compose. When you do the function composition, function with the inverse, you will get x. That was there in 1.8. Now, this immediately means, right, because if you learn for all functions, right, for all functions out there, then clearly sine inverse of sine of a flower is a flower, because these guys cancel each other out. It's what you do for inverses. You have seen this before, right? You have seen ln of e equal 1. Why? Well, because log base e of e is, oh, nah, I don't want that one. I want the e to the ln x. That's the one I want, is x. And ln of e to the x is x. That's the one I want, not the one with 1. All right, so why is this so? Well, again, those are the red formulas, right? Those are the red formulas. And we use this to solve equations, sure, right? But you have ln and e are inverses of each other. So when you combine them in any way, you will get x, because that's the rule for all functions, not just linear or trig, right? For all functions ever. So as you can see by looking at this ridiculous flower example over here, if you are able to match these two, then you are able to solve the problem. Now, in some cases, you will be able to cancel and you don't have to compute. In some cases, you have to compute. So, how much is, let's say, cosine inverse of cosine of 2 pi over 3? Well, right? It's just 2 pi over 3. Now, if you want to show this calculation, right, you will say it's cosine inverse of, and how much is cosine of 2 pi over 3? Right? So you can go into your unit circle, right? Figure out it's right there. All students take calculus. That's a pi over 3 measure in a reference angle. So cosine is negative in that quadrant. So your cosine of 2 pi over 3 is the same as negative cosine of pi over 3, and that is negative 1/2 in this case. So there will be a negative 1/2 in here, and then you have inverse cosine of negative 1/2, and that's just going to bring you back into 2 pi over 3. So this is the way to compute it without canceling cosines, because right, they do cancel each other out because it's an inverse of itself, right? Now you can't just, if they're the same, you can't immediately cancel everything and move, because you have to worry about the principal period, right? And I'm just looking at the next problem. So this was a problem. Well, it's not next problem. It's problem 36. But they're next to each other in the book. And if you take a look at the cosine inverse of cosine of 4 pi over 3, right? If I cancel these, I'm not going to get this as the answer. Actually, the correct answer is 2 pi over 3. Now, again, why? Because of the reference angles. And that's why I don't like to kind of memorize things. I like to analyze these things. So if you draw the circle for this, I was about to say circuit, but circle, there we go. And you have your pi over 3 and your 2 pi over 3 and 3 pi over 3 and then 4 pi over 3. There, 4 pi over 3. So this is your 4 pi over 3 angle. You still see that the reference angle is your reference angle is pi over 3. That stays the same because the closest x-axis, right? Blah, blah, blah. And then all students take calculus. Cosine is still negative in the third quadrant. So when you are computing this, right, the cosine of 4 pi over 3, that's going to be a negative cosine of pi over 3. And that's exactly what we had earlier. And you get negative half. So this turns out to be cosine inverse again of negative 1/2. And we know because of the last problem that that's 2 pi over 3, not 4 pi over 3. So you can't just cancel. You have to be a little bit careful with calculations. But when they swap their order, and you have a trig function on the outside and inverse on the inside, okay, that's the one that you are going to use actually in calculus 2 to figure out something called trigonometric substitution. So let's take a look at these types of problems. Let's say you have something like this, 49. It says tangent of inverse cosine of 5 over 13. So how do we solve this problem? All right, so we set up a triangle and we use pick angle somewhere, and then use the inverse cosine to put the values. Now, inverse cosine is adjacent over hypotenuse, which would make this one 12. 13 squared minus 5 squared is 12. I mean, the square root. So what's the trick? The trick is to actually write the inverse tangent looking at the triangle. And tangent is 12 over 5. So when they cancel now, the answer is 12 over 5. And that's actually what goes here as the answer, 12 over 5. That's what you would type in your in MyMathLab. So when you have these, when you have a trig on the outside, you can set up the triangle and you can solve the problem that way. So I'm going to put down 2 problems for you to try, and then let's see what we can do with graphs. So tangent inverse of tangent negative pi over 6. So that's one problem. And the other problem is, ooh, nice, secant, huh? Secant of sine inverse of negative 1 over 2. Okay. Okay, let's see. All right, so these are the 2 problems. Try both of these. I'll give you some time, and then I'll come back, and we'll go from there. All right, let's take a look at these. So tangent is odd function, and odd function will kick the minus out, and then inverse tangent is odd as well. So this is the same as minus tangent inverse of tangent of pi over 6. And tangent of pi over 6 is root 3 over 3. And then inverse tangent of root 3 over 3 is just going to bring it back into pi over 6. Just as if you cancel them. You can cancel them, actually. And the answer is negative pi over 6 for this problem. So negative pi over 6. I think, yeah, this was 39. I did not write these. I don't know why. And where is the secant? I think this one, 56. Okay. So for the secant, right? You have this negative sign, right? Which you can construct a triangle and then use that negative on 1 and leave 2 as the hypotenuse. So, I need a triangle. So for this triangle, you pick any triangle, doesn't matter. Put theta somewhere. Hypotenuse. So opposite and the hypotenuse. That means that this leg is 2 squared minus negative 1 squared with the Pythagorean theorem, which is square root of 3, right? 2 squared is 4. Negative 1 squared is positive 1, so 4 minus 1 is 3, so that length there is root 3. So now, what's the secant? Secant is 1 over cosine, right? So you want to write inverse secant here. And all you need to do is to look at the sides of in the triangle. And the secant is adjacent, hypotenuse over adjacent. So that's going to be 2 over root 3. Right? 2 over root 3. And now, when these guys cancel, because they're inverses of each other, the answer stays as 2 over root 3, which we rationalize because we don't like root 3 in denominator, and get 2 root 3 over 3. So you can have inverse first, followed by the function, or you can have a function first, followed by the inverse. And there, as you can see, they're solved in different ways, right? On the left side, we compute, and on the right side, we convert, so we can cancel. And they're both great. All right. Graphs and domains. We'll see what that means. So, I mean, maybe I should say domain range. How about that? Let's put it this way: domain / range. Okay. So, how do we graph inverse trig functions? Well, last class we learned how to graph 6 trigonometric functions: sine, cosine, tangent, cotangent, secant, cosecant. And we said if you know how to graph sines and cosines, you just need to flip those graphs for secant and cosecant. And then for tangent, we had those special rules because tangent had the what you call the midpoint, right? Where the other ones had the start point and end point and so on. Now, graphing on inverse trig functions, at least their vanilla state, right? It's literally going to pick the points of, let's say, sine, and then swap their order and then graph them. So let's make the graph for this. So we are going to draw the sine function. We have 0, we have pi, we have 2 pi, we have the top over here at pi over 2, and the minimum bottom at 3 pi over 2. Then there is another one over here, negative pi over 2, right, and negative pi, and it goes forever and ever and ever, right? It never stops. So what is my table of values looking at the sine x? Well, I have the input of x and output of y, which would create my ordered pair points x, comma, y. So let's go with the negative pi over 2, 0, pi over 2, pi, 3 pi over 2, and 2 pi, because we can. So what are the y values? Well, at negative pi, y value is 1. At negative pi, the y value is 0. At negative pi over 2, the value is negative 1. At 0, value is 0. At pi over 2, value is 1. At pi, value is 0. 3 pi over 2, negative 1. And 2 pi, value is 0. So this creates my ordered pairs that I can draw on the graph and then just connect them. So now, inverse. Take these points and flip them, because that's what the inverse does. Replaces domain and range. Well, 0, 0 you can't really flip. And now what you hopefully see is that you have all of these pi values on y-axis instead of having them on x-axis. So I can, let's keep red. X and a y. And let's pick 1 unit and negative 1 unit, because look, your x's are just switching between negative 1, 0, and 1. Just taking one of those values. And then we'll need some tick marks for x and a y, for a y-axis, I mean. And let's go with pi over 2, pi, 3 pi over 2. On the bottom, negative pi over 2, negative pi, going forever. So now, where are the dots? Well, 0 and negative pi. Negative 1, negative pi over 2. 0, 0. 1 pi over 2. 0 and pi. By this time, when we have a normal class, someone yells bingo already. Then we have negative 1 to 3 pi over 2. And then the pi would end up there. Look at the shape. Do we all see the sine function kind of flipped? I hope we do. Now, can you give me one major observation about this red curve? Apart that it's wavy, apart that it's, right, what we already said, it's going up, it's sideways, it's not flat. What is something very important that you can spot on the red graph? Come on, guys. It's not a trick question. Something obvious.
Sorry, can you repeat the question?
What is very interesting, important? What's the really
It looks
important?
like the other graph, but it's like flipped vertically.
Yes, and what did that do to the graph? What did that do?
It changed the domain and range.
That's correct, but in I don't even know how to ask this question because there is something obvious the way the graph looks like, some basic characteristic that we talked about since day one. Look at the graph.
Is it just that it looks like it's rotated?
Well, we said that. We said it looks like it's rotated.
Are you talking about the vertical asymptotes?
Not the vertical asymptotes, but you are getting closer. There are no vertical asymptotes. There are no asymptotes of any kind in a sine function. But something, you are getting closer. You're getting closer. Not there yet, but
And it's not domain and range.
well, they were flipped, right? So, and that's the reason why the whole graph like stood up, if you want to say, instead of being horizontal. Now it's vertical. But what got ruined? What got messed up? What's changed? Like literally, we're talking about that from the day one of this class until today, and you will be talking about the same thing until the end of differential equations. Like, what is
Vertical line test?
okay? What with it? Finally,
It's not a function. It does not pass
that's it.
vertical line test.
Thank you. Yes, it's not a function. Yes. So we started with a sine function, and a sine function passed vertical line test everywhere. No matter where you draw the vertical line, it passes the vertical line test. Draw a vertical line here, fails infinitely many times. So that is not a function. Is it an inverse? Yes, it is. Is it a function? Nope. Not a function. Here, in blood. Not a function. Very good. So now we have to use the restricted domain and chop up this so that we only take a piece which is a function. And we do that in this box here. That's the box that we take, because that box will pass vertical line test. So on the restricted domain of sine x from negative pi to pi, we have an inverse function. So if you go away from there, obviously something is going to bend, and right. So if you take this box here, you see it fails, right? You see that it fails. But if you take, as I said, if you take this box, oh my God, I said pi, or no, pi over 2. What the hell? Pi over 2. There we go. Pi over 2. See? It's pi over 2. Well, that's the input of pi over 2. That's this much right here. Because that's what you are picking restricting domain on the original function. And that because the original function is now chopped up, then the inverse of that piece is the full function. So we are not cutting the inverse. We are cutting the input sign. We're cutting the input sign, and as a result, we are getting that. So now, and you have to do this for all of them. So now if I take a look at my input sign is like this. From negative pi over 2 to positive pi over 2, negative 1, positive 1. And that as an inverse has an inverse function. So now you have your negative 1 and your positive 1 on the x-axis, and your positive pi over 2 going up, your negative pi over 2 going down. So negative and negative are a point, positive and positive are a point, and then they go like this. Curves differently. So now this is inverse function, sine inverse of x. And the reason why this is an inverse function obviously is because it passes vertical line test everywhere. Now, if you put more into your sine function, then that will add more onto the inverse and it will ruin the function. It will not be a function any longer. So that's why it's important. Okay. Now we do that for all 6. Now the most important of all, obviously, would be the tangent. Yeah, I said obviously. It's not obvious yet. When you start taking courses, you'll see. But for now, right, inverse tangent. So let's take a look at inverse tangent. So vanilla tangent, right, y equal tangent x, is going to have those vertical asymptotes at negative pi over 2 and positive pi over 2. And then the tangent is going to go through. And then you're going to have the next one. And the next one, and the next one, and the next one. Right? This is a 3 pi over 2. And it cuts through pi. This one cuts through 0. So how many of these do you have? You have infinitely many. Well, that means that when you draw the inverse of tangent, it will stack up, right? Because remember, we flip, right? So when now your vertical asymptotes become horizontal asymptotes, and the inverse tangent is now going to be sideways, because we learned it's going to flip. But there is more. It's infinitely many of these. And they're all stacked on top of each other. And it's going to go forever. There is another one over here, right? Going through like that. Forever. Is it a function? Hell no. It fails vertical line test, right? But if I do the restrict in the domain from negative pi over 2 to positive pi over 2, if I restrict domain, then that will kill all of these other. I did not label this. That's terrible. That's a 0. That's a negative pi over 2. That's a negative 3 pi over 2. That's a positive pi over 2 going up. So if I chop up my input tangent to only have the principal period, which is in between negative pi over 2 and positive pi over 2, there we go, that would flip into just one of these, and then it is a function. I did not label these guys, because that one is going to pass vertical line test everywhere. And because it's passing the vertical line test, it's a function. And it's going to show up a lot in your calculus later on, so you might want to learn this very well. Every single inverse function has this situation where you have to exclude in the original graph a lot of it in order for the inverse to be an inverse function. I will invite you to break your head. I mean, it is an honors course, obviously. So I am going to invite you to break your head and draw, right, later on when you practice and learn, right? While you practice and learn. Graph inverse secant. So how do you do that? Well, you draw the secant. Wait, how do I draw the secant? Oh, it's the cosine, and then I just need to flip it inside out. I got it. Okay, right? So you draw cosine, then you flip it inside out, then you delete the cosine, and then when you have the inside out graph, you can either use it to get the points of value, or you just know the cosine values are just flipped for a secant. And you can construct the graph, because once you have the secant graph, you restrict it and you flip it, and that's it. So please, if you have any further questions regarding these graphs and things, stop by office hours and we will take a look at it. Now, I do want to give domain and range, right, for at least these ones that I did. And I believe somewhere on the cover of the book, you actually have them all listed. Just let me, I'm flipping right now through this to see where, yeah, here in the end. So all of your regular graphs are there, and then that means that your inverse graphs will be the same, just flipped on the side. So there is at the back of the book, you have all of this. But anyway, observe my domain for inverse tangent. So this is y equals inverse tangent of x. And we have the domain to be all real numbers, and the range to be from not inclusive negative pi over 2 to pi over 2. And that's the domain and range for the inverse, which is completely opposite from the domain and range for the regular y equal tangent x that was on the interval, right, chopped off at negative pi over 2 to pi over 2. So that actually becomes my domain, because I don't go any more to the left or to the right. So negative pi over 2 to positive pi over 2 would be the domain, and the range would be from negative infinity to positive infinity because, right, it goes forever down. Range is y, domain is x. So because these functions go forever down and forever up, they will have that in the range. And yeah, you can do the same thing for sine actually. So over here, you have your domain from negative pi over 2 to pi over 2, and your range from negative 1 to 1. On the other side, they flip. So the domain is negative 1 to 1. Right, that's left and right. And the range, which is up and down, is from negative pi over 2 to positive pi over 2. Once you have the graph, right, domain and range are easy because you can just look at the graph and have those graphs done quickly. I mean, not graphs, the domain and range, right? If that's asked of you to get. Any questions, concerns about the inverse, which is supposed to undo trig? All right. See you later. Bye.